I'm actually going to try to address a little bit questions of aging mortality in biology. But I will also touch on questions of certainly mortality, but also aging in other systems like ones we discussed very briefly, automobiles, but more importantly, as far as I'm concerned, in systems like social organizations, aging of cities, aging of companies, and so forth. And I'll leave that to the end. But all of these, oh, this doesn't work. We have this problem. Well, yeah, I can do it, yeah, yes. Yes. So, these are considered usually biological, and a theory of aging, it seems to me, if you ever get one, has to really incorporate all of these. All of these somehow have to be put together, and my view of this is going to be very systemic and very big picture. So it's very coarse-grained. I'm not going to go into any details. I'm going to cover a lot of territory, and I'm going to try to hook many of these things together, as you will see. From a physicist's viewpoint, a theory means constructing a quantitative conceptual framework that
this will be his stuff.
No. For mechanistically understanding what is going on in aging, and indeed any theory of aging, it seems to me, ultimately has to tell us why we live about 100 years and not 1,000 or 1,000,000 years, and why the same tissue with effectively the same genes ends up, if it's a mouse, living only 2 to 3 years. So this is the kind of grand questions and the grand vision, and I'm going to try to, in a very rough way, address some of these issues. But I'm also going to talk a little bit about, at the very end, I don't know how much time I'm going to leave myself, a fascinating question as to why it is that companies are much like us. They're born, they grow, and they all die like us, whereas cities, by and large, are viable. It's very hard to kill a city. You can drop an atom bomb on a city, and 30 years later it's fine. So cities are extraordinarily robust and resilient, but companies are like us. They have finite lifespans, and as I said, at the very end, I will come back to this. So it was interesting that the question of mammals and the size question of aging came up earlier, and I would use that as a point of departure. So we're all familiar. I will stay mostly with mammals, but you'll see this can be expanded to across any taxonomic group. But we manifest ourselves across this extraordinary scale of sizes, from a few grams all the way up to enormous 10 to the 8th times bigger, 10 to the 8th grams with the blue whale. And we are, to about 80–90%, scaled versions of each other in terms of almost anything you can measure about us. That is, any physiological variable you measure or any life history event you measure scales in a regular way, and the most fundamental of which, of course, is metabolic rate, which has this extraordinary regularity to it, despite being maybe the most complicated, complex process conceivably in the universe. So here's plotted on a log-log scale, a classic plot of metabolic rate, basal metabolic rate versus body mass for a bunch of animals. And it's kind of remarkable because each one of these organisms, each subsystem, each cell type, each genome has evolved with its own unique history, with its own unique environmental niche. And so every point on this, and if you could deconstruct every point, is historically contingent. And yet, they've all lined up on a simple straight line on a log-log plot. Furthermore, this line doesn't have a slope of 1, which would mean that, for example, again, something simplistic, that if you double the size of an organism, you double the number of cells, you would expect to double the amount of energy you need to support it. That's not true. The slope of this is very close to the number of 3/4, which means there's an extraordinary economy of scale. The bigger you are, the less energy you need to support a unit mass of tissue. So many of you are very familiar with a lot of this, but I want to develop this and leading into the question of aging and mortality, but also try to understand where this comes from. because this repeats itself across taxonomic groups and even goes all the way down, indeed, through to unicells, to bacteria, and all the way down to the intracellular level, to mitochondria, and even to the respiratory complex. That line is actually drawn in to be exactly 3/4 and continues all the way up to multicellular organisms. So the summary of that is that metabolic rate scales in this extraordinarily simplistic way. It scales as mass of the 3/4, and which means that per unit mass, it decreases in a systematic way, which means on the average cell, even though it's the same cell in a whale and a shrew, it has a different metabolic rate, which is dependent upon the size of the system, which means that there is a systemic process that is going on that is not to do with the deconstructing it into its basic units. So I will come back to that as we develop it. So as I said, if you look at any physiological variable, they all scale in similar ways, and they all have similar exponents, all simple multiples of 1/4. Here's something trivial. The radius of the aorta scales as mass to the 3/8, which happens to be also the same as the way radius of tree trunk scale. This is heart rate decreasing as mass to the 1/4. This is white matter to gray matter in the brain scaling as mass to the 5/4. Here's genome length. There's much more scatter here, but it scales, you see, as mass to the 1/4 for a bunch of unicells. And I could show you 50 more of these, but the one that we're of interest here is this one, which we've referred to, which is in fact how lifespan scales with body mass. Here's birds, mammals, and invertebrates. And you can see there's huge scatter here, much more than in the others, but it's clear there's a generic trend. And if you believe in statistics, each one of these also has a slope that's very close to 1/4. The birds are a little bit off, but you can see it's pretty good. And by the way, one of the problems here is a question that has only turned up implicitly, and that is the extraordinary difficulty in getting good data, credible data, and data that's controlled. You cannot do controlled experiments on this, and the whole question that was brought up at the beginning this morning of what do you actually mean by mortality, zoo animals versus animals in the wild and so forth. So all of that is we put under the rug, and this is just the data taken from the literature. So I just want to, one thing that many of you are familiar with, if we just take that as an idealized form, for the moment that lifespan scales as mass to the 1/4 and heart rate decreases as mass to the 1/4, we have this intriguing result that roughly speaking, the total number of heartbeats in a lifespan is independent of size. So small things live very fast, big things live very slowly, but in such a way that there's an invariance, something that doesn't change very much in this coarse-grained way of thinking about things. Of course, there's nothing very fundamental about heart rates. Oh, there's data. That's just, there's yet another Levine. And you can see they're pretty good. It's pretty good across mammals. But the important thing is not this result. The important thing is the thing at the top, that actually, at a more fundamental level, the number of times you produce ATP, the number of turnovers of the respiratory complexes is roughly speaking an invariant across aerobic metabolism. So there's another invariant, and that is that the metabolic rate per unit mass decreases as mass to the 1/4, I mentioned a moment ago, and if lifespan increases as mass to the 1/4, that means that the total energy needed to support a unit mass of an animal is roughly speaking the same across all animals, and there's data to support it. And where's Krastan? Look at the journal that's published it. Yeah. So there are these intriguing invariants, and whatever theory you have of aging has to explain all this. So, whatever it is, whether you want to be deeply reductionistic or whether you want to be systemic, it has to explain these. So here's just a summary of all these results. I've summarized an enormous amount of data here, actually. But there's this extraordinary simplicity occurring underneath the extraordinary complexity of life, and they seem to have this universal quality. They have this simple power law scaling with its dominance of a quarter power. And what underlies it? What's the reason? And I'm just going to do 2 minutes of the whole theory. What underlies this is the universality of the networks that sustain life at all scales, whether it's the things like our respiratory system, our circulatory system, our neural system, but also the networks within cells, even networks in ecosystems and so on. The idea is that all of these have universal mathematical and physical principles that transcend the evolved design, because we see this manifestation whether we in plants or in mammals or in fish, crustacea, and so on. So whatever it is, and all of these are supported by networks, and natural selection, of course, has solved the problem of how do you efficiently sustain, in our case, 10 to the 14th cells in a democratic, efficient way on the average. Well, you evolve networks, and those networks have generic properties. That's the idea. So there's just a sampling of them, many of which you're familiar with. That's us, of course. That's the brain, white to gray matter in the brain. That's networks within cells, mitochondrial and microtubule networks. These are networks within mitochondria and so on. And the idea is, whatever the structures are, these have kind of generic, universal mathematical properties. So they have to transcend it. So here they are, ones that were suggested by myself and some colleagues. First is these networks have to be space-filling. They have to go everywhere. They have to supply every part of the organism. The second is that the terminal branch of the network, the capillary and the circulatory system, mitochondria within cells, are roughly speaking invariant with the size. That is, if you change the size of the organism, the fundamental units do not change. In other words, when you evolve new species, you don't reinvent the wheel, so to speak. Natural selection did not reinvent capillaries, did not reinvent a liver cell, and so forth. It built up the network, and that's the multiple variations that we see within taxonomic groups. And the last of these principles that transcend design, which is a very strong assumption or a very strong principle, is that there's some optimization going on, that the continuous feedback loops, mechanisms implicit in natural selection has led to some optimization, and for example, in the case of our circulatory system, to the idea that of the infinitude of possible networks that we could have, we meaning all mammals could have, the ones that we do have that are space-filling and have invariant terminal units are ones that minimize the amount of energy you need to pump blood through the system, the mundane thing of keeping you alive in order to maximize reproductive fitness. Okay, so that's the idea, that's the conceptual framework, and then the idea is to put all of that into equations, and I'm just going to do one minor thing that's kind of just a schematic of a network, but the idea is, I've got to do one thing I do want to stress because it's going to become important when I talk about aging. What goes in here comes out here. There is a conservation law, whatever this kind of network is, except possibly informational ones, which means that the flow in here is just the number, I'll talk about the circulatory system, is the number of capillaries times the flow through the capillary. This is an invariant. The flow into the system is the metabolic rate. So if metabolic rate scales as mass to the 3/4, so must the number of terminal units. So we have this curious situation that occurs throughout biology, and that is that the number of sinks that you're trying to support, number of cells in this case, increases linearly with mass, but the number of sources, the capillaries that feed them, is increasing at a slower rate as mass of the 3/4. And this turns out to be the origin of why you stop growing and why we die with a longevity that increases as mass to the 1/4. Our lifespans increase in mass to the 1/4. So this is important, this mismatch. So I'm not going to go through the mathematics. I'm not going to do a Peter thing and show you the equations other than flash them through. You have to believe that there's a whole bunch of equations. that eventually gives rise to determining the complete characteristics of these networks, that is, how they scale within them, a complete theory of your circuitry system, of any circuitry system, but in particular how it scales from one organism to another in terms of what I want to talk about now. And indeed, out of that comes the scaling of metabolic rate as mass to the 3/4 and all the other scaling laws that I mentioned, and I'm going to focus in a moment on the longevity. And just to show you that this is to establish credibility, there's a whole bunch of predictions. You can see, you can't absorb this, of course, but I just want to show you, flash through the circulatory system, the respiratory system, plants which have a completely different system, but based on the same principles, predictions versus the observations, and indeed even for ecosystems. So just to give you a sense of this theory in terms of its predictive power and its quantitative aspects for making all kinds of interesting other predictions. So I've emphasized that one of the things that comes out of the theory is indeed that a systemic viewpoint that a liver cell in an elephant behaves differently in terms of its metabolic rate than it does inside you or inside a mouse, and this controls all of time scales, the metabolic rate of a cell, and indeed it's been tested. This was a prediction that we made. Here was the prediction of mass to the -1/4. But of course what it says is if you believe this theory, if you remove the network by looking at the metabolic rate of a cell in vitro, then all of these should migrate up to that top line, all having the same value no matter where they came from in terms of the mammals. And indeed the theory predicts that line, not only that it should be flat, it should be the same for all mammals, but indeed the value of it. So this kind of establishes, to my mind, the fact that there is a systemic process that's going on, and the fact that we see a scaling of lifespan with size following the same kind of scaling law is suggestive that it's a systemic quantity, and I will explore that in a moment. But before doing it, it seems to me that if you want to understand death, aging and death, you should first of all understand growth from this viewpoint. What led to this? So here it is. So we know how we grow. You eat, you metabolize, you send metabolic energy, so to speak, through the network to feed cells. What does it do? It replaces those that have died, it repairs, and it grows new ones. So there's the equation in English. So that's what it is, maintenance and growth. And there it is in mathematics, in a highly simplified form, just to make it simple. So metabolic energy, number of cells that are there, metabolic rate of the cell, energy needed to create a cell times the rate at which you create them. And you can put that in terms of the overall mass, and there it is, an equation, and that can be solved. And there's the solution down at the bottom. And you notice it has very few parameters. It has the overall scale of metabolism, the average mass of a cell, and the average energy needed to create a cell. And this is supposed to be true, so to speak, for all organisms. So there's just a small sampling. This is all with the same parameters. And you can see there's 2 mammals, a bird and a fish. And if anyone wants to talk to me about fish continually growing, I'm happy to discuss that. It's an important point of this, actually. But just to show you the universality of it, whether you believe the theory or not, the theory tells you that if you plot it in this Byzantine way, the mass at ht relative to the mature mass, which the theory can calculate, to the 1/4 power, and plot that versus this variable. I'll leave that out for a minute. This is one of a variable that comes out of the theory. This is age, this is 4, this is mass to the 1/4. Everybody should grow in the same way. And this is data, this is just a small subset of the data we've looked at. And by the way, I didn't realize there'd be a lot of talk about cancer, but I actually included this slide. We've also taken this to cancer, which is much more sophisticated because you have to grow a tumor from the host. So it's actually a little more complicated, the equations. But this graph has all those red points are actually tumors, and I'm happy to discuss with anyone later some of that work on the growth. Sorry?
The parameter age.
Very good question. Yeah, I can talk to you about that. That's a very interesting question. The question of the parameters and how they change and so forth. It's more to do with variance, actually, than to do with absolute numbers. Okay. So let me now switch with that background into aging. And many of these graphs, they're ancient graphs. It doesn't matter. I just want to make the point. Many of you have seen these kinds of things. There's survivability of human beings. And the point to be made here is that if you believe this, where we've gone from being like other animals, kind of an exponential decay basically, to this more sigmoidal shape, what you see, there is a maximum lifespan. So I think it's important, we haven't stated that, but it seems to me there is a maximum lifespan, maybe 120 years. I'll leave that out. We had this graph that Leonard showed earlier. I mean, these data, this is a very ancient form of it, but it doesn't matter. The point I wanted to make, which was made, is that we die primarily from things that I would call not disease. I'm neither a biologist nor am I a medical person, but we die from what are, in a certain sense, mechanical things or things caused by damage in some form or another. So this is like Walter's marathon stuff, except my version of it. I found this somewhere, I forget. But the point is that what this is what's called percentage of maximal capacity. And here it is for breathing capacity, vital capacity, renal plasma flow, glomerular filtration rate, none of which I know much about. But here they are. What you see is they all improve dramatically up until we're mature, and then it's a slow road down. And what you also see is that, roughly speaking, that it happens almost at the systemic level in a linear fashion. So these are just some observations that I think are important about confronting a theory of aging and death. First of all, it's effectively universal. I know there's all kinds of questions about exactly how you define, but from this kind of big picture viewpoint, almost everything ages and dies to varying degrees. There seems to be an asymptotic, I call it asymptotic, survival curve, which gives a maximum lifespan, and that maximum lifespan scales approximately like this. I used the 1/4, it could be some other number, but close to that, and so on. But these are the parameters, and the question is, where in the hell do these numbers come from? And indeed, it seems to me, if you have a microscopic theory, one of the questions you have to ask, which I had up at the beginning, is how in the hell do microscopic timescales, molecular timescales, somehow exponentiate up to 100 years, or whatever it is. And secondly, and lastly, we have these invariant quantities. So, my own view has been, in terms of the conversation that's been going on, is that it really is tribological. The tribology, I don't know if you know, is the engineering field of wear and tear. And it's exactly the question of aging of automobiles and so on. So there is some kind of wear and tear, and the view from this viewpoint that I tried to develop is that since we are effectively a bunch of networks, interacting networks, and these networks are flows, and they're flows from the macroscopic to the microscopic, down to the cellular and even molecular level, there's continuous network phenomena all the way through. They're flows, and these are dissipative flows. They dissipate energy, they create entropy, and they do, and by their very nature, create damage. So I'm trying to put this in the most general framework. Now, the most vulnerable part of a network in terms of the way life functions are the terminal units. That is where the interface is between, for example, capillaries interfacing with cells, transferring that energy is a critical component. If the terminal units start to decay, start to have trouble, you are in trouble. Now, you can generalize this, but I want to keep it in this simplistic form for the time being. And so those are, of course, the ones, the terminal units, is where we have the greatest number of vessels, no matter what level, whether within cells or within a multicellular organism. And that is, they're continually being degraded. And of course, they're also being continually repaired. And I will come to that in a moment. But it's the point that has already been said, that continuous damage, that continuous increase of entropy eventually leads to death. But it happens in I would like to argue, in a systemic, continuous fashion. And the trade-off in terms of repair is this one that's also been mentioned, that there's this trade-off between allocation of energy, metabolic energy to repair versus metabolic energy to simply push all the resources, metabolites, and energy through the system, and also to do to be active, to move, to think, and so forth. There is this trade-off between them in order to ensure that organisms live long enough to produce, to maximize their fitness. And lastly, I will define, as you will see, death as the point at which there are a sufficient number of unrepaired or unfaithfully repaired, as I say, damages have occurred. So that's kind of the framework, and I just want to give you a very boiled down version, taking all the network stuff out of it, but all the networks, this is how it was derived through calculating things in the network. But here it is. So I'm sorry, Peter's face there defines the power dissipated in some terminal unit, whatever it is. That's called DET dt. And that's an invariant because the terminal units are invariant. So that's the same across all organisms of the given type. So the number of terminal units scales as mass to the 3/4, I emphasized before. So the total power causing damage is this, and each one of those damages, I mean, we can think of it microscopically as molecules, of course, colliding with inelastic collisions causing damage, whether it's in the physical infrastructure or in the DNA, it doesn't matter. I just want to get a framework established. Each one of those, though, since it's all electromagnetic, is of the order of a typical chemical energy. So it's, in the language I use, it's less than an electron volt, 10 to the 19th, 10 to the 20th joules. So after a time t, this is the number of damages. And that the damage is just calculated from this formula. This is the amount of damage in time t that's being caused. And if each one causes roughly delta E, then that they can calculate the number of damages. And there it is there. And what you see immediately, and the reason I'm going through this, is if you ask how does that change with time and size, then the number of damages per unit mass, if you look at this equation, increases linearly with time, but in such a way that it goes slower and slower the bigger you are in a systematic way. So, in fact, you can do a feedback loop on this because it was mentioned earlier. It also damages the repair mechanisms, and this actually leads to this ultimately exponentiating. But in fact, it doesn't really exponentiate till most organisms are dead. But the point is that the cumulative damage is increasing roughly linearly in time, but there are fewer of them per unit mass the bigger you are. Therefore, big things systematically will live longer. And now I want to do just a little simple calculation of saying, well, I'm going to define this quantity F as the fraction of entities, they could be cells, they could be molecules, that are unrepaired damages before the system collapses. Okay, so this defines a maximum lifespan, and if you do that, you end up with a formula for the maximum lifespan. There it is in terms of quantities that are in principle measurable, in practice almost certainly not, but in principle measurable or well-defined. And from this, what we determine is that lifespan goes as, this is the number, say this is the number of cells, this is the mass, therefore, of the organism divided by the number of terminal units, which is effectively its metabolic rate.
The bigger the better, right?
The bigger the longer you live.
If you about some of us.
Yeah, I mean, the bigger you are, the more efficient you are, the longer you live.
But that's not on the individual organism, right?
Sorry?
Right, that's what we were just wondering.
This is not on the individual
No, of course
organism.
not. No.
This is on a species level.
This is on the species, absolutely. This is on a species level, absolutely.
So you are unsafe.
Yeah, you can't say anything at this stage.
Be positive about us again.
But so I should back off, because the philosophy here is, at least my philosophy is, that you can't mitigate questions of aging and mortality until you have a theory, and being a physicist, until you have a quantitative theory, or something that tells you what in the fuck are the parameters that you can tune to change it. So this is very much the big picture vision of what are the dominant parameters that determine our lifespan, whatever size we are. And I will talk in the next slide. So let me just finish this. So interspecifically, that's your point, that is between species, then it is indeed, this gives rise to this mass of the 1/4 scaling law. But we can also ask intraspecifically, well, what did I do next? No, maybe I just put some numbers in. I'm sorry, yes. I put in some numbers here. And for this, I actually calculated, just as an example, because I have a theory, the theory of the circulatory system, we can calculate how much damage is being produced in the capillary system. So if you do that, lo and behold, you get a number that's, this is not believable in terms of, 50 is ridiculous, but it says of the right order of magnitude. It did not give a number that's 1 million years, and it did not give a number that's 3 months. It shows you why lifespan is the order of tens to hundreds of years, and also where this number comes from in terms of the interface between the small number that's to do with the damage, this delta E, and the very large number of the number of entities that compose the organism. So, we got something else shifted here. So, some of the predictions. We have the mass dependence of lifespan, but we also have the temperature dependence of lifespan, which hasn't been talked about, although it was talked about, ironically, in Peter's talk in terms of glasses, because the metabolic rate, which is, I'll show a slide or two in a minute, the metabolic rate, of course, if you look at it from a molecular viewpoint, a chemical viewpoint, is produced by chemical reactions, and that's controlled by the Boltzmann-Arrhenius factor, which is the e to the e over kt. But importantly, a second thing this predicts, of course, is that if you look intraspecifically, that is, that you keep the mass fixed and ask what happens if I change the metabolic rate, if I shift in the metabolic rate. I'm sorry, it didn't compute properly here. It tells you that the percentage change in lifespan should be, roughly speaking, the percentage change in the metabolic rate. And that's, I know caloric restriction is very controversial and lots of different experiments and so on. But actually, if you look at the data, that is actually pretty good. I showed a moment ago that out of the theory comes that the number of damages goes linearly in time and inverse is mass to the 1/4. And I showed you that data earlier, that decrepitude seems to go in a linear fashion. And lastly, a non-trivial point is that aging is approximately uniform in an organism. Different, or at least within an organ. And that it does occur everywhere. And that comes, of course, out of this because it's a network-based theory with its space-filling quantities. So there's the caloric restriction, which has not come up yet, but the data fits it. The temperature dependence, it says that this is the form of metabolic rate, and that since all rates are controlled by the cellular rate, all of them should in one form or another behave like this. And with, by the way, with the same activation energy, average activation energy, that means that metabolic rate, growth rate, mortality rate, rates of evolution, that is rates of DNA substitution, should all vary with temperature in pretty much the same way with the same 1/4 power and with the same activation energy. That is, there are two numbers that determine everything. One is the 1/4 that comes from the network, and the other that comes from sort of average activation energy, or maybe the average energy to produce ATP. And indeed, here's data on lifespans of invertebrates, fish, other weird things. And what has been plotted here is you've taken the lifespan, taken out the mass to the 1/4, and then taken the log of it, and it should behave linearly with inverse temperature. And not only that, this coefficient is predicted. This coefficient here is predicted, and it should be, the prediction is actually about 7, so it's not so bad. But the fact that it behaves this way, that lifespan can be changed by changing the temperature, I think is another very important, not only observation, but is in fact a prediction of this theory. So I won't talk about repair, but you can analyze repair mechanisms in this format, and I'm not going to do it because I want to do two other things. I'm just going to say it. Repair adds to, you've got to take, I've only talked about damage, but you have to subtract from that the rate at which things are repaired. And in fact, the reason I introduced sleep here and why sleep is related to it is because the brain is an organ that needs special repair, needs something that's different from other parts of the system because it needs to maintain its integrity. And so roughly speaking, the number of damages has to balance the number of repairs. And from that, and using the formulae that I just flashed on, you can determine how long you sleep. And there it is. I mean, the data isn't very good, but this is it versus size for animals. This is sleep time versus awake time on the top. And this is sleep cycle time, REM time, and the prediction for this was 0.18. Both of these should be 0.18. One should decrease as 0.18 and the others. So this is just to give added evidence that this picture makes some sense. So I'm not going to talk about molecular evolution, but it has the same parameters with the same behavior. Again, trying to add to the portfolio of things that the theory can predict that ultimately come into determining age. So I'm going to finish off very quickly with a couple of things which are outside of biology, because the question is, can you apply these ideas? And I'm going to do this extremely quickly. So the first question is, are companies and cities organisms? And if so, why do companies die and cities don't, roughly speaking? Well, here's universality of scaling laws for cities. And this is income, GDP, crime, and patents. There's lots and lots of these. But the interesting thing is they all scale in the same way. They have a universality. But unlike biology, and this is crucial, instead of being sublinear, 3/4 being less than 1 for biology, these are superlinear, being bigger than 1. And that means that there's a positive feedback loop in the way these networks that underlie cities work. And indeed, that leads to, if you do the same kind of growth ideas, to open-ended growth, which is, roughly speaking, what we see. And open-ended growth with no mortality, unless you run out of resources, which is, of course, what we're going to do. Here's companies. This is a data set of just over 30,000 US publicly traded companies from about 1950 to 2010, I think it is, that we analyzed of various things. You see there's lots of variance here, but you see a definite trend, and those red lines are when the data has been binned. And these, unlike cities, are just like organisms. They scale sublinearly. If they scale sublinearly and we follow the same logic through, all of these unlike cities, should stop growing and should die.
But cities should also stop growing because they will reach a point where you cannot deliver.
Yes,
so
we
big,
were
you can deliver goods in the middle of the city.
no,
And
that's
it-
let's discuss that at the end. I mean, in
However-
principle, in principle, there's no stopping. The only thing you have to do, of course, is instead of having 12-lane freeways, you would have to have 50-lane freeways if you had a city of 100 million.
Okay, but then
But
you-
of course, you're not going to do that. So in that sense, yes, but in principle, there's nothing to stop you. So it's not surprising that as yet we haven't reached there. Tokyo is 35 million.
I'm just thinking, like when we developed the vascular system, it was because
Sure.
diffusion of oxygen.
Yeah, so
It's oxidation.
in fact, from that idea that you just brought up, you can calculate the
Right.
maximum size of a mammal.
Right.
And if you do that, you find that it's the size of a blue whale. Okay. So, so just what I said, this is sublinear. If you follow it through, it should have everybody stopping growing, despite everybody thinking that they're growing. Everybody should stop growing, and they should eventually die. And that's all those companies. This is a spaghetti graph of 30,000 companies. And you can see all these Silicon Valley guys are zooming, hockey sticks, zooming up, but they're all going to stop. They all stop, and they all eventually stop. And indeed, let's see, they all eventually die. This is the survivability graph for companies. This is whether they go bankrupt or liquidate or acquired, it doesn't matter. But death, and you can see, it looks just like those that are familiar, and I'll show a graph, for all organisms except human beings that look just like this in terms of
So is the difference competition
come to
cities
me.
and companies?
No, it's not competition. It's to do with diversity. It's to do with diversity and the fact that cities are not only multidimensional, but their multidimensionality is, and therefore diversity, is continuously, monotonically increasing. Companies are going the exact opposite way. They start out with lots of things, and they gradually narrow, and if they cannot change, if they cannot adapt and evolve, they die. TWA, General Motors, IBM, all of these effectively died. And you need special companies that can overcome that. Sorry?
Supreme Court ruled that they're alive.
Yeah, exactly. No, that's why you use the word dead, because they're exactly they were dead as far as most of us are concerned, but they've been legally resurrected. So here they are. These. So one is mortality. On the right is mortality. Is survivability, and just to show you, that's a biological survivability curve. You can see the companies look just like it, but not like us. We were once like this, of course, before hunter-gatherers or whatever. Now, of course, we have this long period of what you saw earlier on the survivability curves. And the last thing I want to show you is, I wanted to show you this too, briefly. This is plotted. Just look at this graph. This is basically the same thing, the number of firms versus their age. And you can see it's a beautiful exponential fall off. It's just like, radioactive decay or something, which is what most organisms do. And the half-life of companies, of US publicly traded companies, is 10 years, so if you, roughly speaking. So finally, to cars, and very quickly, here's the survivability for cars. So actually get some data on these bloody things. And what you see, it isn't like organisms, much like us. It's interesting that a human engineered system actually reflects us a little bit in that it has the shelf here that we have. We, of course, now go out like this, but they're not biological or like companies, mainly like this. And the final thing I want to do, because I don't have time to discuss any of this, I did want to throw this on, is calculate the following, the number of heartbeats in a lifetime of an automobile. So if you say it lasts roughly 100,000 miles, and the average speed is about 25 miles an hour, Therefore, its lifetime is actually about 4,000 hours, is the actual running time. Its frequency, the turnover of the engine, I average, say, 2,500 RPMs. And if you put that together with all these numbers, you see that the number of times that engine turns over, the number of heartbeats, is about 6 times 10 to the 8th, whereas our engine turns over maybe twice as long, but roughly the same order of magnitude. And I put this out as total speculation that the reason that these are so close is because it's to do with material damage. And the overall scale of damage for a single damage is the same, roughly speaking, whether an automobile, who said it, molecules? Was it you that said focusing on molecules? But the fact that they're molecules and that the scale of molecular activation energy and damage energies are of the order of a fraction of an electron volt, roughly speaking. So you could develop from this, and I won't go into it, a little theory to determine how long should an automobile survive. Why doesn't an automobile survive 100? Goes to our question this morning. What determines whether it's 100 years or 2 years or 10 years or whatever? But this is the basis of it. Okay, so I've thrown out a whole bunch of things here. They're all very big picture. There's lots of exceptions and lots of things that I certainly did not go into detail about. But I just want to stress that I do feel, and I come from shamelessly from a physics background, that if we don't understand some of the quantitative aspects and some of the generic features of aging and mortality, we'll never get a theory. So that's just a kind of philosophical statement that you can scratch out from the talk. But I feel that we do need more of this, and I'm hoping that's what this meeting is about, because its title is The Physics of, you may recall. So, okay, so I'll finish there.